And we're going to start today with a presentation by Tim Woodard from NVIDIA on the future of AI and graphics. With no further ado, please. Ooh, sorry, a little bit of housekeeping. Going too fast here. We have a mic in the center of the room. At Q&A, if you have a question, please make use of the mic, but we will also have a QR code that you can use to an application called Slido, where you can type your questions. Please keep your mobile silenced, but handy in case you want to use your mobile device to ask questions. We do, however, recommend using the mic. We'd like to have this more informal, collaborative environment. With that, sorry, Tim.
No, gave me time to get a water and
there you go.
A way to advance slides. All right. Well, hello, everyone. My name is Tim Woodard, and I'm a senior manager at NVIDIA focused on solution architecture. I've been with NVIDIA for almost 9 years now. And in that time, a lot has changed. In fact, I'm a digital twin of Tim. Very convincing, I hope. We'll see how it goes. And so in that time, much has changed. Let's see, am I going backwards? I might be going backwards. Thanks, Bob. There we go. So, of course, we're going to have graphics problems here at an NVIDIA talk. So, before joining NVIDIA, I actually spent 20 years in this industry building visual systems for trainers. And of course, we need these trainers to enable folks to prepare for difficult or rare or costly situations, right? And so we build simulators so we can create these environments that allow us to be sure that when we put a warfighter, a soldier, or any operator in the field, we can be confident that they're going to do the right thing because they've already encountered this situation before. And it turns out that we need the same kind of technology for physical AI. And I'm going to come back to that in a little bit. So a little bit of background. You might think that, with NVIDIA's kind of position right now, that do we really care about computer graphics anymore? Isn't it all just AI? That's all that matters anymore. That's all you hear about is AI. Well, I'm hopefully going to make the case here for you that there's a very beautiful synergy between artificial intelligence and computer graphics. And it's going to have a profound impact on this industry in the years to come. And it's already happening. You may not notice it, but I'm going to point out some things that make this case. So when I started in computer graphics, this was in the late 90s, mid to late 90s. This is my 28th or 29th ITSEC, I think, consecutive ITSEC. That was right when PC graphics began to potentially do what we needed them to do to replace the big iron image generators. So back in the day, we had silicon graphics systems, really big refrigerator-sized computers to drive a single display, right? At that time, PC graphics came on the scene, and it was kind of like that 80 or 90% solution for 10% of the cost. And so very rapidly, that came to be adopted. But I would argue that as you walk around the floor today and you look at examples of image generation for training humans, you're not going to mistake a simulator for reality. There's still that uncanny valley, that gap between simulation and reality that's been difficult to close. And this is in spite of literally now decades of advancement in computer graphics algorithms and hardware. A good example of that is the area of ray tracing. And this was always in my mind like the holy grail. Could we just not ray trace everything? It would be incredible. You can have all of the You look around this room, and to me, this is a good example of where ray tracing would shine, no pun. So you have lots of light sources. You have many different material properties all over, from carpet to steel and curtains and glass. Very difficult to model and render using traditional rasterization. So with rasterization, the idea is you have the polygons of the world, and they've each been assigned a material property. And then one at a time, or in parallel on the GPU, those get converted into pixels that map to screen space. It's rasterization. We rasterize those polygons. And then for every pixel, we compute a color. And the challenge there is that when we're calculating that pixel, we don't really have knowledge about the rest of the world around that pixel. We're processing each pixel individually. And so we've played lots of games, hacks. We have a bag of tricks to try to replicate how light and energy behave in the environment. So things like shadows and reflections that are dependent on the surrounding environment, we can approximate using these tricks. And most of my career was spent trying to hide the artifacts that arise from implementing those techniques. Ray tracing, on the other hand, which is not a new idea. You can see here the first paper on recursive ray tracing by Turner Whitted, published in '79. It kind of solves this problem in reverse and elegantly resolves all of these lighting kind of challenges that I described. So shadows and reflections and things, they just kind of fall out. And the way ray tracing functions is rather than bring all of the triangles into screen space and create pixels, we start with every pixel in the final image that we want to produce, and we cast a ray into the 3D environment. In that 3D environment now, we're asking the question, what's the first object that's intersected by that ray? And once we find that point, we can ask, okay, what are the material properties of that point? And cast more rays based on that to the surrounding environment, recursively bouncing those rays off of all the surfaces until you hit a light source. And then you can calculate all the light that reached that pixel through that object that was first hit and all the ones that were recursively hit. Does that make sense? Are you trying? So it's like exactly the opposite of rasterization. And as I said, all those challenges with recreating a realistic image of the world, they just fall out. What's the problem with it, though? It's very expensive. It's very costly. You need literally hundreds or thousands of rays for every pixel to resolve all of the potential ways that light could reach the eye, which is why you have not seen it until recently in real-time applications. So it was relegated to media and entertainment. If you're going to render out a movie, like Frozen is a good example. I think of this one. That was ray traced, right? So Frozen, there are individual frames in that movie, and this is an old example now, right? Individual frames in that movie that took 45 hours to render on like a cluster of machines. So we're not going to ever see this in modeling in sim when we need 60 frames or 120 hertz, 240 hertz. There's systems now with 360 hertz. You can't, it's not practical. You need 360 days to render out this movie. And so I would say that the unexpected thing that happened in the last 10 years that enables ray tracing in real time is artificial intelligence. So if you look at modern games and applications that use ray tracing, in many respects now they're able to outperform rasterization, particularly when the scene gets really complex. So this is an interesting part of how ray tracing functions. It's not linearly affected by how many objects or how complex the environment is. So it's really more affected by how many pixels you want to generate in the final image. This is a very subtle point, but what it means is you can have environments with billions and billions of objects rendered at the same basic performance as something that is much simpler. So now we have this mechanism that allows us to ray trace these really complex environments in real time. And the way that works with AI is that we train a neural network to, given just a few ray samples in the environment, we can train it to infer what the final image would look like. And maybe you've heard of this technique, it's called denoising. So normally with ray tracing, we're not going to render all the rays. We can't afford to render all the rays. So we render some of the rays, and you get this really grainy image. But if you kind of squint, you can imagine what the final image would look like. Well, the AI has been trained on millions of examples of the input image that's grainy and what the fully rendered image would look like. And it can learn to translate them. Right? And so that's the piece that we didn't have that's made ray tracing possible. If you followed what we've been doing at NVIDIA for the last 10 years or so, we focus on something called domain-specific architecture. So domain-specific architecture is where we're going to dedicate a part of the chip to accelerate a specific function that's important for the class of problems we're trying to solve. So a great example of that is tensor cores. So you've heard of TP, like tensor processing units, tensor cores. Is that a familiar term for you all? So in AI, it's fundamentally built on mixed precision matrix multiply add operations. And tensor cores are just really fast at that. That's all they do. Similarly, we have ray tracing cores, which answer that question of what object did a ray hit. And they do that really, really fast. So these are domain-specific parts of the chip that you can take advantage of to make these techniques that would otherwise be impossible, by orders of magnitude impossible, they can become real time. Okay, so why does NVIDIA care about this right now? AI is everything, right? What's graphics have to do with where NVIDIA is going? Well, we have this kind of core belief at the company that in the future, everything that moves is going to be autonomous in some respect. Everything. And that autonomy will be driven by artificial intelligence. Now, the difficulty with that is that unlike other forms of AI, perhaps you've used large language models like ChatGPT or something similar, we have a huge corpus of data with which to train those models. And that's obviously what AI requires, is you need to have lots of data to train AI. But when we talk about the physical world, how things move, interact, how energy behaves in an environment, we don't have that kind of data source to train these models. And so if we're going to have autonomous systems that learn how to operate in an environment, much like we have simulators to train humans how to operate in a particular environment, we have to have simulation. It's the only way. We have to simulate the world. Before we're going to deploy, let's say, a robotic system. And let's use a simple example like for warehouse logistics. You're going to have an AMR, autonomous mobile robot, that's going to move items from one area of the warehouse to another. You want that robot brain to have encountered every potential condition it might encounter, right? What if boxes fell into the aisle? What if there's a pedestrian moving about? Or some other kind of change in the conditions of that space. Before you have that system, especially those that are going to coexist with other humans, we want to be very comfortable that they're going to do what we need them to do. So before we field it, we have to validate, right? We have to validate that these systems are going to work correctly. And this is much like what we do with a simulator for humans, and an instructor is going to test, is the pilot ready, right? So we build simulators, but the challenge is that for validation, if we're going to validate a robotic system, we want the fidelity level to approach reality. It needs to be hyper-realistic. It needs to be physically accurate, physically based. And so this is why NVIDIA has a huge focus right now on graphics, because we need to create these hyper-real environments for autonomous cars and drones and delivery bots. and healthcare. So there's like surgery robots. I don't know about you, but like if I'm going to have a robot remove some of me, I want it to know how to recognize that thing, right, and stitch it up correctly. That's just me. Okay. So you have to have simulation to validate that that system is going to behave, and it needs to replicate reality. So the bar is very high for realism there. And so the way that we can achieve that is through artificial intelligence. And this is where we have this virtuous cycle right now. How many of you have heard of deep learning supersampling, or DLSS? So this is a popular concept in gaming where the application that's going to render an image is only actually rendering about 1 out of every 16 pixels that make it to the screen. And so that enables now, because AI is able to upscale and produce additional frames of video, that enables it to run quickly enough that we can produce enough data to train an AI model. And then using more of that graphics, we have more data to train the model, and so we have this kind of virtuous cycle. So in this way, we can kind of say, and I'm going to see if I do this the right way. Yes. Okay, good. So there's kind of this symbiotic relationship between graphics and AI. What we've been working on lately is a technique for generating more realistic environments using what we call world foundation models, where we take millions of hours of video from the real world, millions of hours, from cars driving around, from factory environments, you name it. And we train an AI model to kind of empirically understand how the world works. So rather than having to have a computer scientist figure out what's the right math for how light and energy behave, how do physics work in this space, we just give the AI tons of examples, and it learns that environment. And then from that, we can now create models that can transfer between a computer-generated image, which can be of very low fidelity, into many, many, many outputs of the same physical structure of what we rendered. Many, many example outputs that are physically accurate and look realistic. So, with a text prompt, you have a cartoon image come in, and you say, I want to turn this into a rainy day. It's overcast, and it will produce an image that if you were to walk by it, you would think that it's real. Now today that's kind of expensive. It requires a fair amount of GPU horsepower to produce that. But we're willing to do that right now because we need to create all this training data and validation data for robotic systems. But I think if I go back to the last slide, what you'll see is kind of an interesting trend. In 2016, how many of you know about like the DGX system that we released back then? It was hand-delivered to OpenAI. Jensen signed it for Elon, hand-delivered it. It was the first computer that we had built that was specifically designed for accelerating artificial intelligence, less than 10 years ago. And so the reason I've gone through this whole history lesson is because if we're going to think about where might we go in the next 5 to 10 years, I want you to kind of project forward a little bit. So this year we released something called the DGX Spark. Seen the DGX Spark? There's actually a few out on the floor. So the DGX-1 weighed about 75 pounds. It cost, adjusted for current prices, probably about $300,000. It consumed a lot of power. It generated a lot of heat, and it had 1 petaflop of compute performance. A DGX Spark is about the size of a CD. Do you remember CDs? I'm sorry. About the size of a CD and a little thicker, maybe like a Mac Mini or something, about that size. It runs on a couple hundred watts of power, like a wall wart brick, and costs about $4,000, and has the same computing performance as the original DGX, a petaflop of AI compute. And so what is expensive now, like with these transfer models to create these hyper-realistic environments using AI, I believe probably in the next 4 or 5 years is going to enter the world of real time. And that is going to absolutely transform how we create training systems for humans as well. We'll no longer rely on artists and computer scientists to have to fine-tune every aspect of a simulation. We're going to teach the AI with mountains of examples that are produced from our existing simulation systems to be able to replicate those environments in addition to the real world. I think that's where we're headed. Can we really predict where we're going to go in 5 years? Probably not. 5 years ago, we didn't even have large language models. So like ChatGPT didn't exist. We're on about a 1-year cadence now with architecture updates, which is double the speed from where we had been. So I'm excited to come back in, 5 years from now, 2030, and we'll see what the next big thing after that will be. But I expect by then it will be possible to walk around the floor and not be able to tell if you're looking at a simulator or if you're looking at reality. Any questions? I threw a lot out there. Yes. There's a microphone right there in the middle of the room.
So something you mentioned that I thought was very interesting. Is this on? Okay. Something that I thought was very interesting was that you said that a simulation that would be used and understood by autonomous systems must have high fidelity. Mm-hmm. Why don't you think it's possible for a system to identify what's relevant and necessary and exclude that irrelevant information to the task at hand?
So that's a wonderful question. So this is where there's 2 roles that simulation plays when we're building physical AI systems. The first is creating synthetic data by which we train the perception models to understand the world. And there's a lot of debate about how much fidelity is required there. You can use potentially lower fidelity data to train the AI model to learn how to recognize objects or segment the environment. So one of the use cases would be an autonomous car. It has cameras, right? And it needs to know every pixel in that input stream. Is it a pedestrian? Is it a sign? Is it a car? Is it a road marking? In fact, it can be useful to have lower quality data to train the AI system. But when we go to validate it, we want the validation to replicate the real world with all of its complexity and fog and issues with the sensor. There's perhaps rain on the sensor, cracks, pixel problems, all these kind of things we want to be able to replicate as realistically as possible, because if we're going to field that system in the real world, we want the validation to match the real world. So there's kind of 2 different roles of simulation there. And I think on the training side, you can get away with lower fidelity. But if you're validating, you can't.
I highly understand that. I'm actually working on a project where I'm simulating degradations of cameras through self-driving cars.
Absolutely, yeah.
Yeah, right now what we're trying to do is classify uncertainty when it comes to these and the risk associated with that uncertainty. So that was a good question. Thank you so much.
Appreciate it.
I don't have a question so much as another data point for your slide up there. In 2009, I was at Microsoft Research Labs working on the Microsoft Connect project. Everybody remember the Connect? So we had to train it. We'd already shipped Xboxes all over the world, and we're trying to teach it what a living room was, which sounds really simple to us, but at the time, we didn't even have really good GPUs for the first machine learning system that I ever worked with. But back then, it was 224,000 hours of CPU time just to help it build this little system that could recognize the human body and how to use the body as an interface device, but also recognize the things in a real
So it's
way.
doing like pose estimation and environment detection, right?
Yep, but that's how far we've come on this spectrum.
It would be interesting to like go back and take that model today, and with the data that you used to train it, how quickly could you run that on a modern system? It would probably be laughable, like how much time it took then versus what's possible now.
But the other thing that was really interesting is the brain, because the Xboxes were already out there. They only had 100 megabytes of available space. So that entire AI brain ended up being about 60 megabytes.
That's incredible. So that the DGX Spark I mentioned, that little tiny supercomputer that you can set on your desk and run from wall power, it has 128 gigabytes of unified memory. So it's kind of like, what was that famous saying back in the day? Nobody will ever need more than, how much RAM was it? Like 640K or something like that?
You kids today are spoiled.
Yeah,
with all this
yeah.
AI.
Hi, so I had a question as like from the perspective of a student attending the conference. I wanted to point back to a point where you said that AI would have to change a little bit on how graphic designers and computer science majors or people in that field would operate. I wanted to know what your vision for the future of those people in those careers would be with the enhancement of AI, and would it be used as more of a tool to aid them in what they already know, or would they have to like go and get more specialized degrees in order to like keep their jobs?
Great question. So I still think that it's very important and valuable to have a traditional education when it comes to things like computer science. You need to have an intuitive understanding of how algorithms function, how the hardware functions. So computer science and computer engineering still wildly important. However, there's also now a new tool available to you. And so I, as a computer scientist myself, I wrote lots and lots of C++, right? And I had a project last year. In fact, we worked on a paper that we presented here on doing 3D reconstruction of the world from images. So kind of like a new approach compared to photogrammetry. Maybe you've heard of Gaussian splats and neural radiance fields, right? A lot of AI is driven by Python, and I'm not a Python programmer, but I understand how software works. And so rather than go, spend a couple weeks learning Python and all the syntax rules, because they don't use semicolons and tabs. Indentation is what defines scope, and very irritating as a C++ programmer. I hate it. And it's very amorphous. So I didn't want to learn Python, but I knew I needed it. And so I used a language model to describe the algorithm. This is what I want to do. Because as a computer scientist, I understand what I want. I understand how loops work and searching and sorting, right? So I described to the AI what I'm trying to do. And it got me some Python code in about 10 seconds that 99% of what I needed. I was able to make a few tweaks, and now I had the application that did the work that I needed in this area of Gaussian splats and radiance fields. And it made me hyper-productive. So I could have spent weeks and weeks going and learning maybe a new adjacent skill, but I was able to use AI to translate the skills I already had. So it doesn't, I don't think AI negates in any way the need to develop your own abilities and skills as a student. You've got to have that really, I think, intuitive understanding of computing. But now you'll be able to apply that knowledge and understanding to other domains that you might not otherwise been able to without AI.
Thank you.
Hi there. So everything you talk about is very visual based, which makes sense based on rendering and graphics. However, when we talk about getting to creating actual simulations that will really replicate a physical environment,
Yes.
There's a lot of things going on that you can't see. And so, whether it's electromagnetic spectrum type things or even just different frequencies of light that our eyes wouldn't be able to see, those things do still then present themselves in the real world with real physical effects. So from a military standpoint, we do a lot of electronic warfare kind of things.
Non-visible spectrum stuff.
Exactly. And so do you see how this would be able to be applied to create these simulations replicating the real world environment, yet with things that you cannot see? And how would that work?
Yeah, so this is a huge area of focus right now in research with AI. If we're going to have physical systems, so talking about robotics, they don't work in the visible spectrum exclusively. There's LiDARs, there's radars, there's other kinds of sensors that have to function. And so what we can do, though, is develop validated models, right, which we already do this today, validated physics models for how energy at a particular wavelength is going to function and interact with an environment. And use that simulation that we trust to create a mountain of data, right? So given all the different conditions of material properties and weather conditions, we can produce a mountain of data to then train an AI to infer how that sensor or that energy is going to propagate in an environment. Much like we do with the visible spectrum, it's the same exact concept. You just have to have example data to train the model. And again, that's where I say simulation is still important. We have to do things in the classical way to produce the data that we train the model with. So we call those surrogate AI models. And that's used for all manner of physics. So how does a ball bounce on the ground can be trained this way. Computational fluid dynamics, right? That's very, very computationally expensive problem. Even with acceleration, GPU acceleration, if you're trying to do CFD models for like the wing of a plane, you need a very high level of fidelity, and that takes maybe a weekend to go run on a supercomputer. Well, we can train, using that simulation, we can create the training data to produce a surrogate which can now operate in real time. So that absolutely is very much in the focus of what we're working on when we're building these AI models.
Cool, thank you.
Welcome.
All right, folks, thank you very much. This concludes our session. Tim, thank you very much for
Thank you.